You see those permanent magnets made from iron? Great, but what if I told you that according to the classic physics, those little things are completely impossible? The physics of Isaac Newton, falling apples and orbiting planets, the physics that built our bridges and sent us to the moon is super clear on this. Ferromagnetic materials cannot exist, and yet we're surrounded by them. What's going on? To solve this puzzle, we have to leave our intuitive world behind and journey into the bizarre, confusing, and often backward world of quantum mechanics with its surprising mathematical mess. To really get why ferromagnetism is a quantum miracle, we first have to understand why it's a classical impossibility. Why did the brilliant minds who figured out motion, energy, and electromagnetism get completely stumped by the magnetic properties of iron? The problem comes down to a simple, elegant proof from the early 1900s called the Bohr-van Leeuwen theorem. Basically, the theorem proves that if you use the laws of classical physics, the total magnetism of any material at normal temperatures has to be zero. Always. No exceptions. It doesn't matter what it's made of or how strong a magnetic field you put it in. Once things settle down, all the magnetic effects should just cancel out and disappear. No electric motors, generators, transformers, or electromagnets. Why? In the classical view, you've got two options for where magnetism comes from. First, the electrons orbiting the nucleus of an atom. An electron is a charged particle, and a moving charge is a current. Any loop of current creates a magnetic field. So every orbiting electron should turn its atom into a little electromagnet. The second source is the electron itself. Classically, you could picture the electron as a tiny spinning ball of charge. That spin would also make a current and a magnetic field. So in this picture, an atom is like a little solar system with spinning planets orbiting a sun, all creating tiny magnetic fields. This is, by the way, not how quantum theory describes it. Spin has no classical counterpart. Picture a solid piece of iron packed with trillions of these little atomic magnets. To make that iron a magnet you can stick on your fridge or use as core in electric machines, a whole bunch of those tiny magnets need to line up and point in the same direction. Their fields would then add up to create one big, strong magnetic field. But the problem is that the world we live in is full of heat, which at the atomic level is just everything constantly jiggling and vibrating. And heat is the enemy of order. It's like a room full of tiny compasses. If it were absolute zero with no heat, you could line them all up to point north. But as soon as you add heat, they all start shaking. The hotter it gets, the more violently they shake. Any alignment you had is immediately scrambled. The compasses would end up pointing in every random direction, and their magnetic fields would cancel out completely. The Bohr-van Leeuwen theorem proves this random, jumbled state is the only possible one according to classical physics. The thermal energy at room temperature is more than enough to overwhelm any weak magnetic forces between the atoms. Chaos should always win. There's just no classical reason for these atomic compasses to all agree to point in the same direction and stay that way. And this isn't just a small error, it's another total failure of classical physics, kind of like the ultraviolet catastrophe. It tells us our everyday understanding of the world is missing a huge piece of the puzzle. To find it, we have to seriously upgrade our old picture and look at things in a totally new way. Stay tuned for the long-form video for the full story. Allow a few months before the video is ready. See you